So now we will see an application of the above result. So let G be equal to GL and R, right? Then G is a group and has a topology. Right. So we claim that G is a topological group. So let's check that. So we need to show that GL and R cross GL and R to GL and R, the multiplication map is continuous. Right. So now note that this has the product topology. Right. So in particular, we know that the projection maps are continuous. So we can look at the projection maps GL and R. This is some PI, right? And let's say on GL and R we have these continuous maps which project onto the coordinates. So let's call this Qij's, right? So given a matrix A, this map Qij, it sends it to Aij. Right? Yeah. So this implies that the composite of these two is continuous, right? So therefore we get that from GL and R cross GL and R to R. So A comma B maps to Aij, or similarly Bij, these are continuous, right? And this multiplication map M, the coordinates of M, are polynomials in the functions Aij and Bij, right? And we have seen that if we take a collection of continuous maps and we form any polynomial using those continuous maps, so like, yeah, so then the resulting map function is continuous, right? So this implies that M is continuous. Right. So similarly, let's take GL and R. Let's look at the inverse map. This A goes to A inverse, right? So we know the inverse is given by this formula, 1 upon determinant of A into adjoint of A transpose, right? Yeah. So now once again, the determinant does not vanish on GL and R. So 1 upon determinant is a continuous function, and this adjoint of A transpose, this is also, each of the coordinates is a continuous function in the coordinates of this GL and R. Therefore the product is a continuous function, right? The inverse is continuous, right? So this implies that GL and R is a topological group. Right? Now let P be this parabolic subgroup. So here we have a R cross R matrix, here we have 0, and these can be anything, right? So we are looking at all P contained in G is equal to GL and R, right? Be this subgroup. So all elements in G cross in G which look like this, right? So clearly P is a closed subgroup. Right? It is given by as the inverse image of the projection onto this piece. Projection of 0 on the inverse image of 0 under the projection onto this piece. Okay, so therefore P is a closed subgroup. So this implies that so this thus the previous discussion shows that G mod P is a Hausdorff topological space. So now we want to identify G mod T. We want to give a nice description of the points of G mod P, which is what we are going to do next. So for that, consider the map. From G, so this is phi, to R dimensional subspaces of Rn. Right. So let's call this set script G. Okay. So here, what is the map? So let's take a matrix A and let's write A as V1. The VI's are the columns of A up to Vn. Right. So since A is in GL and R, so G is GL and R. This implies that the column vectors of A are linearly independent, so we just send it to the span of V1 up to Vr. Right. Now we claim that phi of A is equal to phi of B if and only if there exists P in P such that, okay, so let me just write T, a matrix T in our parabolic subgroup such that B is equal to A times T. Okay, so let's see this. So if there is, we take two matrices A and B such that B is equal to A times T, right? So then clearly phi of A is equal to phi of B, right? Because as if we take B equal to, write as W1, W2 up to Wn, right? So this is equal to V1, V2 up to Vn times this parabolic subgroup. This is R cross R, 0, and here we can have anything, right? So this will show that this is A times T, right? So this will imply that the W1 up to WR are linear combinations of V1 up to VR, right? And both are R-dimensional subspaces, right? So this implies that the span W1 up to WR is equal to V1 up to VR, right? So this shows that phi of A is equal to phi of B. Next, let's assume that phi of A is equal to phi of B and then show that, right? So if phi of A is equal to phi of B, right? So then we have that the span of W1 up to WR is equal to the span of V1 up to VR, right? Now since the W1 up to Wn, they span Rn, and V1 up to Vn also span Rn, right? Since Wi's and Vi's are a basis for Rn, this implies that there exists a unique T. We have a unique matrix T in GL and R, which can be obtained as follows. So what we do is we write each Wi, so W1, W2, Wn, we can write it as a unique linear combination of the vectors V1 up to Vn, right? So if I write W1 as lambda 1 V1 plus lambda 2 V2 plus lambda n Vn, right? So then the first column of T will be lambda 1 up to lambda n, okay? And this matrix T clearly has to be in GL and R because we can do the same, we can replace the roles of W and V, and the composition, the resulting matrix T prime that we get, that's going to compose with T to give identity, right? Right. So the ith column of T is the unique way to express Wi as a linear combination of the Vj's. Okay. Okay. So we just have to show that T is in P. So note that since Wi, we are given this information, right? That implies that is in the span of V1 through Vr, right? So this implies that the ith column of T is going to look like, so this is R, right? And then everything will be 0, right? So, and this happens for I lying between 1 and R, right? So this clearly implies that T belongs to P, right? So clearly, so this proves this claim. We have proved this claim. So let's call this 1. Next, the second point we want to show is clearly phi is surjective, right? So phi is this map from GL, a matrix A, it goes to the span of the first R column vectors, right? Now, given any R dimensional subspace of Rn, we can choose a basis for that R dimensional subspace and V1 up to Vr, and we can extend it to a basis of Rn, and correspondingly we can get a matrix A, right? As any basis V1 up to Vr for an R dimensional subspace can be extended to a basis V1 up to Vn for Rn, right? So which implies we can take the matrix A to be V1, V2 up to Vn. Okay, so this shows that phi is surjective. Right. So this implies that. So when we put together 1 and 2, one can easily check that we have this map phi to script G, right? And this factors through G mod P, and this map is a bijection. Let's call this phi naught. This easily follows from 1 and 2, right? That phi naught is a bijection. So thus the points of G mod P are in bijection with R dimensional subspaces of Rn, right? So which means, so using this bijection, we can give this space of R dimensional subspace of Rn, this set G, we can give G a topology. Right. So we identify G with G mod P using this phi naught, and a subset of G is open if and only if its inverse image under phi naught is open. So clearly, so G mod P is a topology, and this bijection, using this bijection, we can transfer the topology. Okay. So this topological space is called the Grassmannian of R dimensional planes in Rn, and it's denoted Grassmannian R, n. Right. So by the proposition we proved, we know that G mod P is host of, yeah, we get that Grassmannian R comma N is host of, right? And further note that also, so note that GLN R plus surjects onto this Grassmannian R comma N, right? Because why is that? So given an R dimensional subspace, right? So given an R dimensional subspace, we chose a basis V1 through Vr for this subspace and we extended it to a basis. So we get this matrix A. So if the determinant of A is negative, then we just take the last column and put a minus sign. Take, instead of Vn, we just take minus Vn, right? That's one, right? And we had seen, right, as GLNR plus is path connected. This implies that this Grassmannian is path connected. Right? And similarly, the Gram-Schmidt orthogonalization process implies that ON, the orthogonal matrix, surjects onto this Grassmannian R comma N, right? So why is this? So we have ON, this sitting inside GLNR, right? And here we have this map phi to this. So we claim that this composition is surjective. So why is that? If we take any R dimensional subspace, so first, so we can choose a basis V1 up to Vr. Then applying the Gram-Schmidt orthogonalization process, we can get an orthonormal basis for this, and then we can get orthonormal basis for this subspace, and then we can extend this to an, okay, so let me just write that, yeah, and extend to an orthonormal basis for Rn, right? So we get W1 up to Wn, right? So then the matrix A we need to take here is this W1, W2 to Wn, right? Since the Wi's are orthonormal, we will get that A transpose A is equal to identity, right? Which will imply that A is in On, right? And now, so this G is actually equal to G mod P, right? Now, as On is compact, right, since it's a closed and bounded subspace of Rn square, so this implies that, and On surjects onto G mod P, this implies that G mod P being the image of a compact space, it is compact, right? So thus we have proved that the Grassmannians is host of path connected and compact. Yeah. So we can also do a similar construction for complex Grassmannians. Right. So there we will take r-dimensional complex subspaces of Cn. Okay, and in the same way we can show that this is Hausdorff in a similar way, path connected and compact. Okay, and before I end, let me just mention that when r is equal to 1, the spaces Grassmannian 1 comma n are also known as projective spaces and denoted PNR or PNC. So if we take complex projective spaces, so depending on the underlying field, if we can do this entire construction for the real numbers or for complex numbers. So if we are, this is the real projective space and this is complex projective space. So we will end this lecture here.